This next example is a slight extension of the ideas we discussed in the previous example problem. We have 2-point particles, both having positive electric charge. We have a plus 10 and a plus 3 millicoulomb point charge. And initially, the two charges are separated by a distance of 25 centimeters. But the 3 millicoulomb point charge is released from rest and allowed to be pushed away by the Coulomb force. So the 3 millicoulomb charge will begin here, but it accelerates away, and we are asked, how fast is the 3 millicoulomb charge moving when it is a distance of 1 meter away from the plus 10 millicoulomb point charge? We're also given that the 3 millicoulomb point charge has a mass of 20 grams. The first thing I'm going to do for solving this problem is to convert all of the quantities given to the base SI units. So the mass of 20 grams will be 0.02 kilograms. The 10 and 3 millicoulomb point charges will be 0.01 coulomb and 0.003 coulomb respectively. And the initial separation between these charges is 0.25 meters. The final separation between the charges is 1 meter. To answer this question, we are going to use delta PE is equal to Q delta V. When I work with this equation, Q is the charge of the particle that is moving. At any given moment, only one particle is allowed to move in a problem. In this particular problem, we only have two particles and only one of them is moving. So the charge of the particle that is moving is 3 millicoulomb point charge, so Q will be 0.03. The electric potential, the delta V in this equation, is created or set up by all the charges in the particle that are not moving. In that case, the charge that's not moving in this problem is the 10 millicoulomb point charge. V initial is the value of the electric potential right here due to the 10 millicoulomb point charge. V final is the value of the electric potential right here due to the 10 millicoulomb point charge. So when I plug numbers into this equation, I could say delta PE is equal to the charge of the particle that is moving is 3 millicoulombs, or 0.003 coulomb. And I will have V final minus V initial due to this 10 millicoulomb point charge. So the electric potential due to a point charge is KQ over R. So I will have 9 times 10 to the 9 for Coulomb's constant. The charge of this particle is 0.01 coulomb. Our final distance between the particles is 1 meter. Then I'll subtract 9 times 10 to the 9 times 0.01 divided by 0.25. The initial separation between these particles. When I plug these numbers into a calculator, I find that the change in potential energy of the system between the initial moment and the final moment will be negative 8.1 times 10 to the 5 joules. Because we have a drop in potential energy, I could infer that we will have a corresponding increase in kinetic energy. So if the change in potential energy is negative 8.1 times 10 to the 5 joules, I could infer that the change in kinetic energy will be plus 8.1 times 10 to the 5 joules. Now we just have to ask, given this information, we know what is the change in kinetic energy. How fast is this particle moving when it gets to the final position? To answer that question, we'll have to look at what was written, and the problem itself states that this particle is initially at rest. So if I think of change in kinetic energy as KE final minus KE initial is equal to 8.1 times 10 to the 5 joules. Because this particle was initially at rest, that is like saying its initial speed was 0. So I could right away say KE initial is going to be 0, and therefore I could write 1/2 times the mass of the particle, which is 0.02 kilogram times V final squared is equal to 8.1 times 10 to the 5 joules. And when I plug these numbers into a calculator and solve for the final speed of this particle, I get V final is equal to 9,000 meters per second.